Thanks everybody for having me on your course. It's really a huge pleasure, it's an honor for me to speak directly after Eric, because actually reading Eric's book was the thing that really got my thinking going down this path. And so I want to start with a recommendation, which is read Eric's book. I know he's got more than one, so for the avoidance of doubt, the only one I've read is the one called The Origin of Wealth. It's a spectacularly good book. And I know one very experienced, very authoritative economist who told me he wished he'd read it 30 years earlier at the start of his career instead of a long way through it where he is now. So that's a recommendation. To emphasize one thing, I think you'll have heard some of what Eric said sound maybe a bit philosophical, but the point I want to emphasize is that his starting point is the facts. The starting point is, what do we know about how the economy works? What do we know, what does the evidence say about the assumptions that we make? Are people utility maximizing agents? Do we all have perfect foresight of the future? Does the economy behave like a system in equilibrium? The evidence says it doesn't. The evidence is really, really strong on those points, and those are the factual points. So anything else that flows from that might sound philosophical, it's all starting from those facts, which are really crucial. So the reason I've given my talk this particular title, The Policy Implications of Complexity in the Economy, is that complexity is there in the economy. We don't have a choice about whether it's there or not. It is. The choice we have is whether we recognize it and how we respond to it. Now, I'm not at all concerned with what name you give to this, whether you call it complexity economics, as many people do, or whether you call it something else. I don't mind who takes credit for it, because I'm not an academic, so I don't have to worry about those things. I just care about how does it solve problems. What kind of thinking do we need to help us get stuff done? Because that's what I do in my day job. I try and solve problems. So I was thinking, how do I talk about the relevance of this to policy? And I thought, let's state the policy problems that we have in the most general terms that we can. So how do we change things? How do we create new things? How do we value things? And how do we actually make decisions? That's what I'm going to try and walk us through, share a bit of my thinking. Before I get into any of those questions, though, what's actually different about complexity economics? Well, Eric has already described that very well. And he already mentioned an ecosystem. And I think for me, this is the easiest way to think about the difference between what you could call traditional or mainstream economics and the emerging new thinking of complexity economics. Now, I should say there will be people that say, perhaps rightly, that saying that old economics is like a machine is giving it a caricature. Now, that may be true, but I think a lot of the way that I see economics being used to inform decision-making every day actually is using that very basic kind of economics that you might learn at GCSE or A-level. So I think the question we have to ask is, what is the economy actually like? Is it like a machine, or is it like an ecosystem? So a machine is static, it never changes. It's very predictable. You can predict precisely what it's going to do, depending on what you ask it to do. The relationships between its components never change. However complicated it is, they all relate to each other in the same way. It's got a limited range of future states, and it's only got one purpose. So it can either work nicely, or it can fail when you might need to fix it. An ecosystem is very different. An ecosystem is always changing. It's not precisely predictable ever. The relationships between its components are changing and evolving over time. And the range of its future states is unlimited. It's something we'll come on to. And does it have a purpose? Well, it has many purposes and none. Everything in that ecosystem might have purposes of its own, but the whole thing altogether doesn't have any purpose. So you can't really say, is the ecosystem working, or has it failed? Or could it be better or worse? None of those questions are really meaningful. Each of its possible states is just different. And very importantly, as Eric said with his whirlpool example, the form emerges from the interactions of the components. You can't just extrapolate it from the behavior of one of them. So for all of those reasons, I think it's useful to think of the economy like an ecosystem. Now, just briefly, why was it that economists in the 19th century thought that the economy was like a machine? Well, at the time, they thought everything was like a machine. They'd been inspired by Newton, and they thought the universe worked like clockwork. And even the theologians of the time talked about God as the divine clockmaker. So that is actually how they thought stuff worked. It took about 200 years after Newton for Henri Poincaré to come along and say, actually, if you've got 3 mutually orbiting planets in space, after about 100 million years, you can't predict their motion anymore. It's a chaotic, it's a complex system. So if just 3 rocks in space are a complex system, given long enough, then I think the economy probably is as well, because there's a lot more than 3 rocks in it, and some of them have freedom of choice. So first thing we'll talk about is how to change things. And here the characteristic that I mainly want to concentrate on is the economy is a dynamic system. It's a changing system. It's not a static one. This guy is really the founder of the field of system dynamics. And what he said is, effectively, change is all about feedbacks. Systems of information feedback control, fundamental to all human life and endeavor, from biological evolution to space satellites and everything else. And I think there's a good case that he's right. Now, there's only 2 kinds of feedback, so this is a way of thinking that is actually not very difficult to get your head around. It's a simple way of thinking that helps explain very, very complex behavior. So reinforcing feedbacks accelerate change, whether you're talking about population growth, asset price growth, or market share of a new technology. They all have this same characteristic that change leads to more change. So sometimes that can be growth. My rabbit population example, the more rabbits you have, the more rabbits doing what rabbits do, the more rabbits you have next, and you have that exponential growth curve. Works just the same with collapse. Arctic sea ice area has been following exactly this graph on the bottom. And it's because the more the Arctic warms, the more the sea ice melts, the less reflectivity you have, and the more heat it can absorb. So that's reinforcing feedback causing a collapse. So reinforcing feedbacks accelerate change, balancing feedbacks slow down or prevent change. And the best example of one of those is a thermostat. Everybody has one at home. If it gets too hot, it makes it colder. If it gets too cold, it makes it hotter. And your body has exactly the same thing going on inside. It keeps you at 30 whatever it is degrees. So there's loads of these things in living beings, in ecosystems, in the climate itself, and in the economy. These things slow or prevent change. Now, the interesting thing is it only takes one of each of these feedbacks combined to produce a massive range of complex system behaviors. You can have a system like this where, as well as the rabbits, you've got some foxes, and the foxes like eating the rabbits. Well, depending on the relative strength of those feedbacks, you can get any of these kind of system behaviors here. Now, the thing I want to point out is that one of those system behaviors corresponds to equilibrium. It's that red line in the middle, where the reinforcing feedback and the balancing feedback exactly balance each other. Now, that's just one of that huge range of possibilities. Obviously, there are more. I didn't draw them all. And one thing you can see straight away, not only is that just one possible state, but it's probably not very likely. If these feedback loops get out of balance at any time, it shifts to a different state, and there's no guarantee it would ever get back to that equilibrium. So equilibrium thinking is a special case. Complexity theory is a general case. So I think that's why it can explain a lot more. To give an example of where this is useful, this is Steve Keen, who's an economist who actually built a model that did predict the financial crisis. The reason he was able to do that was his model was a dynamic model. It didn't assume equilibrium. It was actually a very simple model in design. It only had a handful of equations, a handful of parameters, unlike the models used by treasuries and banks. But despite those mainstream models have thousands of parameters, but because of their equilibrium assumption, they actually excluded the possibility that anything like the crash could happen. So that's a bit like having a sort of weather forecasting model that rules out the possibility of a thunderstorm, because it assumes that every day will have the average weather conditions. So if you have that, you're not going to do very well at predicting storms. Steve Keen's model actually showed some very interesting behavior about 10 years, I think, before the crash happened. So when we were at that middle bit there with the small wiggles, that's when Gordon Brown was saying this is the end of boom and bust. And lots of economists around the world were saying this is the great moderation. Our theories are so great that we've completely fixed it and the economy is going to be great from now on. And Steve Keen was looking at it and going, well, that's interesting. In my model, that's the calm before the storm. And it turned out he was right. And he's so frustrated with the state of mainstream economics, he's taken to making cartoons, which is where I get that picture from. So that's a very macro level example. But to give a more sort of micro example, this is one that's very close to my heart because for the last 5 or 6 years, I've been working on climate change. Now, carbon pricing is the main policy that most economists recommend to deal with climate change. It's not the only one, but it's sort of top of the list because it prices the externality. Two main ways you can do it. You can have a cap and trade system where you cap emissions and trade emissions permits, or you can have a tax, and maybe a tax and dividend, where you tax everybody for the carbon they use and you give them back the money. Now, nearly everything I've ever read says that these two policies are equivalent, except that one has certainty about the price and the other has certainty about the emissions reductions. I think they're absolutely wrong. In dynamic terms, these are absolutely not equivalent, and I'll show you why. If you have a cap and trade system of carbon pricing, then right in the middle of it, you have this balancing feedback. The carbon price goes up, more people invest in decarbonization, demand for carbon permits goes down, demand goes down when supply is fixed, that means the price goes down. So that means if I do the right thing, I will reduce the incentive on any of you to do the right thing. That's a balancing feedback, so that's guaranteed to slow down change. So what do we see? Well, not surprisingly, the EU carbon price crashed, bumped along the bottom for a long time, has carried it on doing that up until we brought in a load of reforms to make it more like a tax, which is what we have done. If you have the alternate model, the carbon tax, where you give people the money back on a sort of per capita basis, then the more tax we pay, the more investment there is in decarbonization. That means more investment in decarbonization means less tax revenue to give back to everybody, which means the net tax each firm would pay would go up, so the incentive on it to do the right thing has gone up. So under that system, if I do the right thing, the incentive for any of you to do the right thing has increased. So in dynamic terms, that would get us a much, much better result. Now, I don't have a nice example of the effect of that to show you because hardly anywhere in the world has done it. But in the UK, we've gone halfway there. We have a tax with no dividend. So it doesn't have the positive feedback, but it doesn't have the negative one either. And that's been so effective, it's actually helped us have a whole day without coal for the first time in 130 years in our power system. It's been stunningly effective. And this is another way of showing the effect of that same policy, but to illustrate a different thing about dynamics, which is tipping points are incredibly important. Tipping point is some point in the system, either side of which the system's behavior will be very different. It might be that when you pass it, you activate a new feedback, or you dramatically change the balance of strengths before feedbacks, so something very different happens. What we did here, we did something that actually you might think is quite obvious. We had a flat carbon tax, which is the blue shaded bit on the left-hand graph, that added to the EU traded carbon price, which is the grey bit. And for a time, it made coal more expensive than gas in our power system. Where it crosses over the red line is where it did that. Roughly around about that time, what do you see happening to coal? Black line on the right-hand graph, it comes down by 75% in about 5 years. I think that is probably the single most effective climate change policy of any major country anywhere in the world at any time. I might be wrong, but I haven't seen a better one yet. That's incredible. That's why the UK has a really, really good story to tell on emissions reductions. This one policy that just happened to cross a tipping point. So I think if we understand system dynamics, this is the kind of thing that we can do deliberately, again and again. That'll get us speeding up. So, second policy problem, how to create things, by which I mean things that didn't exist before. How do we do innovation? And here, a particular thing I want to concentrate on, a characteristic of the system, is its unlimited range of future states. And I'll explain what I mean by that. Now, as Eric said, one of the ways you can think about how much more prosperous we are now than in the past is by how much the diversity of solutions available to us has increased. There's been a massive increase in diversity. I think that's a good way of thinking about it. So you might think that that would be a primary concern of economics. How do you increase diversity? How do you create things? But if you think about what is the definition of economics, if you look it up in the dictionary, it says it's the study of the allocation of scarce resources. That's actually quite a different problem. Now, if you go, it hasn't always been defined that way. If you go back to a Greek guy called Xenophon, who wrote the first book that was about what came to be called economics, then he said there's two good ways of looking after your family firm, or your farm, sorry. One is to make good use of your existing resources. The other is entrepreneurial creativity. Take some bets, go out and do something new. So he said both of those things were important. Later on, you had Austrian economists who talked about this as the difference between static or allocative efficiency on the one hand, dynamic efficiency on the other. And more recently, we have Brian Arthur, who's a leading complexity economist, who calls it the difference between allocation and formation. So there are lots of people that have thought about the difference between these two things. And the reason I like to show it as an apple pie, just because if you think about it, how you divide up the pie is pretty important, but how you make it in the first place is also critically important. In my family, we've always thought of both of those as very important problems. So Brian Arthur says the same about the economy. The problem of allocation is how quantities and prices of goods and services are determined within and across markets. The problem of formation is how did those goods and those markets get there in the first place? And how did they change and grow and change structurally over time? Obviously, that's really important too. So how did we get stuck thinking only about allocation? As one of the Austrian economists said, from the 19th century onwards, economics more or less forgot about the problem of formation. Why would that have happened? I think it comes down to the maths. Your problem of allocation here is really simple. If we've got 5 of us and we want to share out the apple pie, we can have 1/5 each. You can solve it with an equation, just like a nice Newtonian mechanics equation. Get a nice easy answer on your calculator. Problem of formation doesn't have any nice, neat mathematical answer. There's no optimal way to make an apple pie. It's a process. A whole load of different things need to come together and happen over time. And there's an unlimited range of different kind of pies you could make. So there's no optimal one. You can't describe it with an equation. And because they wanted to describe all of economics in equations and make it a precise science, then they had to leave it to one side because it was too difficult. So I think that's how we've got where we are. But I think we really must not stay here, because if we want to get good innovation, different kinds of growth, the structural change that we might need for sustainable prosperity, then we've got to think about formation as well. So the moral of this is don't just think about the pie slice, bring back the wooden spoon. Rehabilitate the wooden spoon. Now, the first thing to recognize about formation in the economy is there's a hell of a lot of it happening. Eric's already talked about this, so I won't go over it too much, but just from maybe a few tens of different goods and services in the Stone Age through to millions of them now. And if you include all the different variations of each good and service, then it's probably tens of billions of them now. The other thing to notice is that the rate of increase in diversity is increasing. This is accelerating very dramatically. And I think there's a stat that says 97% of our prosperity, the increase in our prosperity, happened in the last 0.01% of our history. So that's how fast this change is happening and these new things that are coming along. So clearly, we have a huge interest in understanding how this happens. If you have an economic theory, if you have economic models where technological progress is exogenous to the model, which means you make up a number for it and stick it in from outside like an assumption, that tells you absolutely nothing about how this process works. So that's obviously not ideal. Can we think of a better way of understanding how this works? Does complexity theory have something to offer? I think it does. I think the economists who think of the economy as an ecosystem think of change in it as a process of evolution. And this slightly fuzzy bit in the middle here, very low tech, took a picture of it in the book, Eric's book actually, and I emailed it to myself. This is by an economist. Sorry, thanks. You probably know the guy that made this, so you should do that. He's called John Holland, and he's a complexity economist, thought very hard about evolution. And what he's noticed is that evolution creates change in two ways. One is replication and the other is mutation. Replication, you can think of as this adaptive walk on the fitness landscape. It doesn't make very big changes. What it means is, you know, the things that are doing well, the beings that are being successful in their environment replicate themselves more frequently than the ones that are not so successful. So that leads to some incremental change. But at the same time, you've got mutation, which happens randomly, mutation in genes. And from that, you get these random jumps that take you much further across the fitness landscape. Just to explain this, this landscape is a sort of theoretical construct where the higher up you are, the better suited you are to your environment. So then the really interesting thing that John Holland found is that evolution splits its resources between those two processes, which he called exploitation and exploration. And how it splits up its resources depends on where the population finds itself. If the population finds itself on a nice high plateau, it's doing really well in its environment, then it sticks all of its resources into exploitation. It milks it. If it's down in a valley having a really tough time, getting beaten about, then it sticks a lot more of its resources into exploration. It jumps further afield. It looks for new stuff. Now, I find that really quite intuitive. And I was thinking, what's a nice intuitive way I can talk about this? And I thought, well, maybe compare a cow and a wildebeest. And the cow is there in a nice big meadow full of green grass. It doesn't have to go anywhere. It can just stay there and get fat and enjoy itself. And that's what cows do. If you're a wildebeest, you've got to escape from lions. You've got to go and find some water and deal with drought and maybe deal with poachers as well. So that's why they go on these big migrations, which they're very famous for. Unlike cows, no one's ever heard of the Great Migration of the cows. I know that's a bit anecdotal, so I'm going to add another anecdote, which is I'm a big fan of Formula One, and I was very happy when someone joined my department who used to work for my favorite Formula One team, which is McLaren. And this guy used to be one of their top engineers. So I said to him, sometimes you have big changes in regulations from one year to another. You know, they say the cars have got to be much safer, or they've got to do without a load of the aerodynamics that they used to have, or they're no longer allowed to have traction control. Other years, the regulations stay exactly the same. I said to him, which years is it when you get the most innovation? The ones where it all changes, or the ones where it stays the same? He said, well, obviously, it's the years when the regs change. That's when we all have to work really hard. And that's when we come up with the good new ideas. So I think this is a critical principle for us to be aware of. And the crucial thing here is that this is a theoretical difference from the old way of looking at it. The old way of looking at it is your regulation, your constraint is something that introduces inefficiency into the economy. Now, there might be things that qualify that view. You might say it gives big confidence to investors. So there might be reasons you want to do it. But on the most basic level, you would only regulate if you're fixing a market failure, and you do that to the minimum extent that you need to fix that failure. Whereas here we're looking at its effect and we're saying, in fact, having a constraint can be intrinsically a good thing because it can shift the balance of resources from exploitation to exploration. Now, very quickly, two examples of where I think this is happening now in the economy. This one is in the auto sector. And what you can see on the left is that over the last 10 years or more, the EU has had much stricter regulations than the US for vehicle efficiency standards. What you see on the right is over roughly the same time, the EU industry's share of total global auto sector R&D has gone up by nearly 10 percentage points. I think that's a spectacular achievement at a time when, of course, China's putting loads of money into its auto sector. Meanwhile, of course, the US share has gone down. So I think what that indicates is the European industry is being made to work a lot harder by those tougher regulations, while the US one is being allowed to sit on its backside. Second example is much more backed up by evidence, you might be glad to hear. And this is about the cost reduction in solar panels that's happened over the last several decades. Over the last 60 years, the cost of solar PV modules has come down by a factor of nearly 3,000. That's quite spectacular. There's this study on the right looked at over a 30-year period what's contributed to that cost reduction. They looked at lots of small factors and built them up to get an overall picture. And what they found was that from a government's perspective, you can look at it this way, that about 20% of the progress was achieved by public R&D. About 60%, 3 times as much, was achieved by what they called market-stimulating policies. In other words, it was the policies to create demand that led industry to put their own money into R&D, to learn through doing, and to achieve economies of scale by building big factories for them. So that's hugely significant because it says those demand-side policies, they're not just costs that are worth paying to fix a market failure. In fact, regardless of whether there's any market failure or public purpose out there, those demand-side policies were the critical thing for pulling through innovation. So it's not about fixing the market failure, it's about, as my friends at IIPP say, market shaping. Market shaping is what can accelerate innovation. So now we've talked about how to speed up innovation, I want to quickly talk about where's it going. Because innovation will always have a direction. Now, I'll have to explain this picture on the left a little bit, I expect. I don't know how much people have come across the idea of technology neutrality, but very often when we have to convince an economist that we should be allowed to intervene in a market to achieve some kind of objective, then if they agree, then they say, yes, but as long as you're technology neutral in your policy. And what that means is don't advantage one technology over another. Now, I think if you're dealing with a machine, that makes sense. That's fine. You want a handle on your machine. Doesn't matter very much whether it's a wooden handle or a steel handle, as long as it does the job a handle should do. That's technology neutrality. Fine. But if you're in an ecosystem, that doesn't work at all, because every single part of it is interacting with every other part. Those relationships are changing over time, constantly. Nothing ever stays the same. Everything you do has influence. So I think one thing I've always found is if you talk to any actual technologist about the idea of technology neutrality, they always say it doesn't exist. They always have deep skepticism about that idea. That's what I've found in the ones I've spoken to. And I imagine if I went and spoke to Dory the fish in her ecosystem and said, I'm going to intervene in your ecosystem, but I'll do it in a way that is fish neutral, I think she'd say, what the hell is that? Anything you do is definitely going to advantage some guys and disadvantage some others. So that might sound quite academic, but why does that matter so much? It matters so much because of the path dependence that you have in the system. And the weather is the most obvious example of a highly path-dependent system that we can talk about. The butterfly effect is what people have called it, that a tiny, tiny change in initial conditions can have enormous differences a little way down the line. And that's the reason that you don't get weather forecasts more than 5 days in the future, because the path dependence is so high it magnifies differences that are too small for us to measure. So the weather's a very obviously path-dependent system, but in fact, as I mentioned earlier, so are rocks in space. Even the position of the planets in the solar system, if you go far enough forward, you won't be able to predict them. And there's an astrophysicist who gave an example of this. He said, if you move your pencil from one side of your desk to the other, then you might have just changed the position of Jupiter from one side of the sun to the other in 10 billion years' time. And that's serious. He wasn't joking. That's what path dependence does in complex systems. And the weather and the solar system, they're very definitely complex systems, but I'm not sure if they're adaptive, because I don't think water molecules and planets change their strategies very often. The economy clearly is adaptive. It's not just complex, it is adaptive too, because we can all change our strategies depending on how the environment changes around us. And so in that sense, I think the economy might be inherently even more path dependent than the weather. So that means we forget the idea of neutrality, think about direction, and think about it consciously and deliberately. And this is, Mariana's very succinct way of putting it. Innovation is political. It is, because every choice you make about the technology will decide the direction you go in. And this on the right, this is from Michael Grubb, who works in this building, gave a lecture in this room, I think, a couple of weeks ago. And he's just looked at for energy futures. In fact, if you look at what are the possible scenarios we could have, you find they, to the best of our knowledge now, they cluster around two very different directions, what is called a green direction and a brown direction. And that's just one illustration of this, that we're at a moment of path dependence. The choices we make now will decide which of those two routes we go down. I think I might need to speed up a little bit, so I'll try and do that. But before I leave the question of how we create things, then really quickly this point about unlimited future states. I think this might be hugely important. Stuart Kauffman is a theoretical biologist who's thought about this, and he did a thought experiment. How long would it take for the universe to explore all possible proteins of length 200, proteins along a string of smaller molecules, amino acids? And he looked at what's the fastest rate the universe could create proteins if it bounced all particles into each other and if you ignore all the distances that might be in between them. And he said even if it did that as fast as it could, the time it would take the universe to explore all possible proteins of length 200 is 10 to the 67 times the current lifetime of the universe, which is 10 million trillion 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 times the current lifetime of the universe. That is a bloody long time. Even more importantly than that, as soon as you actually expand that state space that you're exploring, then the unexplored space increases even faster. That's maybe not so intuitive, it's not so easy to get your head around, but you can think of it as having a load of Lego bricks, and you imagine, first think about all of the things you can make with one step, sticking two things together. Then think about everything you could make with 2 steps, then 3 steps, then 4 steps. Every time you increase that step, the amount of new things you could create goes up enormously, exponentially. And that's what's happened as we're increasing the diversity in the biosphere, in the economy, in the universe. That adjacent possible, the amount of things we could do next, increases even faster. So the more we explore, the bigger the area is that we haven't yet explored, and the smaller proportion of the known area we find ourselves in. So what does that mean? To me, it means very clearly there is no optimal pathway through time. The economy has far more states than we will ever explore. So there's absolutely no such thing as optimality. I think there's a poet who put this extremely well, who said, "Traveler, there is no path. The path is made by walking." And I think that's absolutely true of the economy. There is no optimal pathway through time. We just have to figure out where we're trying to go and strike out in that direction. So on to the third problem, how do we value things? And there's going to be our old friend Bill Nordhaus in this, who seems to be cropping up quite a bit today. But before we get to him, 2 quick characteristics that we need to worry about. One is uncertainty. I'll skip quickly through this because we've already talked about it. But if there's an unlimited range of future states for the ecosystem and they've got unknown probabilities, then quite obviously you can't really quantify the value of those different states with any meaningful kind of confidence. Second thing is heterogeneity. If you've got a machine, then you can think of it as an economy with one agent, with one purpose, and only one good. And in fact, that's what some of the big, enormously complex macroeconomic models actually do. They have one representative agent who's a producer and a consumer of just one good. I don't know who thinks the economy actually looks like that, but that is what they do. If you think about the ecosystem, you've got many agents with many purposes, many goods and services and qualities for all of those things. And that means the value doesn't exist. Value is not intrinsic to anything. Value only exists contingently. It depends on who you ask, on what they have and what context it's in and what they want to do with it. So to give an example, imagine you've got a big clump of seaweed like up in the top left there. Maybe for some little bugs, that seaweed is their home, it's where they live. Maybe for a small fish, it's a good place to hide from the big fish. And maybe for the big fish, it's a nice thing to eat for lunch together with some fish. What's that seaweed worth? What's its value? Well, it depends who you ask. There's no right answer. And that's a characteristic inherent to these kind of systems. Now, what happens if you ignore that fundamental uncertainty and that contingency of value? Well, this is what happens. This is Professor Bill Nordhaus, who won a Nobel Prize recently, co-wrote the book Economics with Paul Samuelson, so you might think he knows what he's talking about. But it turns out that he's worse at maths than my 7-year-old daughter, because this is his first attempt to figure out the costs and benefits of, the costs, in fact, of climate change. And obviously there are a few things he didn't know, which is fair enough. So his first term is minus 10 billion to plus 10 billion. Then he's got a small plus or minus. Then he's got a plus, then a question mark, then some numbers, then another question mark, so on, another question mark. And then what does he do? He actually adds them all up, and he gives an answer to 3 significant figures. I remember my maths GCSE teacher cared a lot about significant figures. She would have murdered me if I'd ever done this. I did a special experiment just for this lecture. I gave my little girl a sum that said 2 plus 2 plus question mark equals what? And I said, what do you think of this question? And she looked at it and said, it doesn't make sense. She's right. Of course it doesn't. It makes absolutely no sense at all. This is the biggest pile of bullshit I've ever seen. And it is criminal. Criminal that he got away with it, criminal that they gave him a Nobel Prize. The sad thing is, it's not just him, so it's not personal with Bill Nordhaus, I promise. This is what the White House Council of Economic Advisors said in autumn 2013. Look at the language here. They're working out the social cost of carbon. This is the value to society of reducing 1 ton of carbon. And you've just got to admire this language. Today we're issuing updated values, technical corrections, estimated using the best science available, rigorous evaluation of costs and benefits. But what actually was the best science available saying at the time? Well, to me, this is the best that was available in the blue. If you take into account catastrophic damages and the fact that we might be averse to those catastrophic damages, then the value of the social cost of carbon is somewhere between 0 and infinity. Unless you want to come up with a number that represents willingness to pay to avoid human extinction, which you can do if you like. Bill Nordhaus probably has. Now, where do I go with that? Well, what I think that means is, sometimes people say, well, it's still helpful to have a number, isn't it? Surely it's always better to have a number than none. I think that's mistaken. That's deeply mistaken. There are 2 things that matter here. One is expert judgment, and in this case, the expert judgment is in the minds of the scientists, so those are the people you should ask. And the other is democratic choice. How much do we care about this? What are we going to do? What Nordhaus has done, and these guys have done, is replace expert judgment with guesswork and democratic choice with arbitrary choice. He's made a choice about how much this matters to poor people, rich people, old people, young people, people here, people in India. He's chosen all of that, but you can't see it because he just did it arbitrarily and stuck it into his model. So the paper that I took that table from, Funtowitz and Revetz, it's called The Worth of a Songbird. It's a very, very good paper. And they said, this is deeply unethical. You're actually taking arbitrary choices, they called it doctrine reinforced by guesswork, and dressing it up and giving it a veneer of scientific precision, which it absolutely doesn't deserve to have. So what happens if you do that? One thing is, I think we tend to underestimate the risks. We make these kind of choices accidentally and arbitrarily instead of deliberately. And the other thing that we might do is underestimate the opportunities. I think if we'd been thinking this way at the time when the first work was done that led to having the internet, if we just said, well, don't pick any winners, let's keep a level playing field, we'd never have got anywhere. If we want to create whole new playing fields, then we just have to get out there and do something. Now, good, just about keeping up. How do we make decisions? Well, in brief, you have to put all of this together. Now, what do we have? This is sort of the standard decision-making tool that we have in government, the Green Book. It's used as the basis for economic analysis. The main thing it suggests you use is cost-benefit analysis. Cost-benefit analysis, of course, has the disadvantage that it's not able to think about dynamic interactions. It's very limited by the problem of uncertainty. You have to try and quantify things that you can't. And of course, it exists within the market failure framework, which it doesn't necessarily go as far as we need it to if we want to create whole new markets. But the great thing is, it recognizes those limitations, and it says, cost-benefit analysis is a marginal analysis technique. It's only appropriate if you expect nothing to change, basically. If there are potential non-marginal effects or changes in underlying relationships, then you need to do something different. So if non-marginal change is your aim, we need to think about what do we do. So how do we decide how to decide? How do you know whether it's the Green Book, cost-benefit analysis, or something else? Well, I think you have to understand what are the characteristics of the problem or the system that you're dealing with. You have to look at it and say, well, is it static over the time period I care about, or is it changing a lot? And are the relationships in it fixed and linear, or are they evolving and non-linear? Is there a disproportionate relationship between cause and effect? Is the range of future states limited, or is it completely unlimited? And is there high uncertainty and high heterogeneity, or do we more or less know what's going to happen and it doesn't really matter what different people think about it? That thinking through it in that kind of way, I think, can help you decide whether you're okay with a fairly simplistic, mechanistic understanding of the economy and the tools that flow from that, so which is your optimizing models, your cost-benefit analysis, and your market failure framework, or if you've got a complex adaptive system, a dynamic system, where all the interactions and the uncertainty and the change and all that stuff matters, then you want to think about simulating models, models that don't make any prior assumptions. They just try and simulate, copy as best they can, how is this part of the economy really working? And there you might want to use systems thinking, which was all your feedbacks and stuff that we saw at the beginning to understand how change happens. And your conceptual framework for this would probably be market shaping rather than market fixing, where you'll think very hard about what new markets do you want to create. But just as an example of how this has already influenced government thinking, I worked on the industrial strategy in my last job, and one of my things I just found most interesting was when an economist came in and presented a slide saying, what's the sensible industrial strategy, and gave us 3 reasons. Rationale number 1 was, don't have a strategy. The market can figure it out best by itself. That's the orthodox economic view. That's his words, not mine. Number 2, the more recent view, government should help in sectors with comparative advantage, which means carry on doing what worked for us well in the past. Okay. Number 3, the more enlightened view, apparently, government should help specific sectors if that addresses some kind of market failure. Now, I'm proud of our Prime Minister and our ministers who supported this and that wrote in our industrial strategy that a truly strategic government must do more than just fix the foundations. It must also plan for a rapidly changing future look to shape new markets and industries and build the UK's competitive advantage. In other words, think about how the world in the future might be different from today and different from the past, and try and be good at the stuff that's going to matter. And if you do that, then the role for government, I think of as being to strengthen this reinforcing feedback between investment, innovation, cost competitiveness, and market growth for new technologies. And you align everything you're doing with that desired direction of travel. You focus on your points of maximum leverage. And if it works well, then not only do you increase your share of global markets, your competitiveness, but you also solve a few policy problems along the way. And this is what happens when we get it right. Solar expands 10 times faster than the mainstream analysts thought it would. Why do we need to get it right a lot more often? Well, because human civilization evolved during a highly unusual period of climate stability. And if we want to keep anything like that safe and stable climate that we enjoyed for the last 10,000 years, then we need the mother of all non-marginal changes. We need emissions to start going down instead of up, like two sides of a triangle. That's insanely difficult, and we're not going to get that right unless we start thinking in dynamic terms. So finally, if you're an economist, or if you think you might meet any economists, or if you think you might be affected by any economists' work, the decisions they inform, then I'd encourage you to ask questions. And you can ask, for this thing we care about, for whatever it is we're talking about, how long will it take for change to be non-marginal? And if we're aiming for growth, what direction of growth are we trying to go in? And how have you predicted the things we know least about? And how have you valued the things that we care most about? I think those questions will always get you some interesting answers, or at least a very blank look, and then you'll feel good about yourself. Thanks.